So for example, the sum law states that if the limit as x approaches a of f of x equals L and the limit as x approaches a of g of x equals m both exist, then the limit as x approaches a of f of x plus g of x equals the two limits, L plus m. That's the sum law. Let's just prove this using epsilon delta. So let epsilon greater than 0 be given. We need a delta greater than 0 such that the absolute value of f of x plus g of x minus L plus m is less than epsilon whenever 0 is less than x minus a is less than delta. Okay, so we can rewrite this just a little bit, just rearrange them. So we have that so this is just rewriting this to combine the f and L and the g and m, okay? So what we have is that this equals this, okay? And then this, we know, is less than or equal to, the absolute value of a sum is less than or equal to the absolute value of each of the summands. That's the triangle inequality, right? That a plus b is less than or equal to a plus b, okay? So we're gonna make this less than epsilon by making each of these less than epsilon divided by 2. So it'll just be epsilon divided by 2 here, epsilon divided by 2 there. This whole thing will be less than epsilon. So we have that epsilon over 2 is greater than 0, and the limit as x approaches a of f of x is greater than L. We know that those two things are true because they were given, right? We're assuming that these both exist, and then what we're wondering is what can we add them in some way? So we know that f of x equals L exists. So because of that, we know that there is a delta 1 greater than 0 such that the difference between f of x and L is less than epsilon over 2 whenever x minus a is less than delta 1, right? Similarly, we know the same thing is true for g of x equals m. There exists a delta 2 greater than 0 such that g of x minus m is less than epsilon over 2 whenever x minus a is less than delta 2, okay? So now we're going to do basically the same thing that we did in the last proof. So we just let delta equal the minimum of those two deltas, delta 1, delta 2. So notice that if x minus a is less than delta, then that means that it's less than both of these, right? This is the same thing that we did last time. And therefore, if x minus a is less than delta, because that means that it's less than delta 1 and less than delta 2. But if it's less than delta 1, that means that f of x minus L is less than epsilon over 2. And if it's less than delta 2, that means that g of x minus m is less than epsilon over 2. So using the triangle inequality from before, we have that f of x minus L plus g of x minus m is less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus m. That's the triangle inequality. We just showed that f of x minus L plus g of x minus m is going to be less than epsilon over 2 plus epsilon over 2. So we've just shown that what we started with is less than epsilon when x minus a is less than delta. To summarize, we have that so by the definition of the limit of f of x plus g of x equals L plus m. Okay, that proves the summation law. So there are 5 basic limit laws. I'm not going to bother proving any more. If there's any that you want to see us prove, let me know in the comments and we can do it. So if c is constant and the limit as x approaches a of f of x and the limit of x as x approaches a of g of x exist, and all of these limits are as x approaches a, then 1, the limit of f of x plus g of x equals the limit of f of x plus the limit of g of x. That's the sum law. The difference law, the limit of f of x minus g of x equals the limit of f of x minus the limit of g of x. The constant multiplier law is that if you have the limit of a constant times f of x, that equals the constant times the limit of f of x. The product law is that if you have the limit of f times g, that equals the limit of f times the limit of g, and the limit of f over g equals the limit of f over the limit of g, if the limit of g as x approaches a does not equal 0. Just for a simple little example, if we have a couple of functions, let's just make them up. Okay, so let's say that this is f and this is g. So let's just see if we can eyeball it, figure out what a couple of these would be using our rules. So if we had the limit as x approaches -2 of f of x plus 5 times g of x, what would this limit be? So using our rules here, we can split this up into the limit as x approaches -2 of f of x plus 5. Okay, so first we applied the sum law, and then we applied the constant multiplier law. So the limit at -2 of f of x, this is one of those examples where it approaches one number even though the value at -2 is another number. So the value of this would be -1. And then the value of g right here at -2, it looks like maybe 1/2. And g is just straight there, continuous. So at -2, g would be -1/2, and then it would be times 5. So it would be -1 plus -2.5, so it would equal -3.5. Okay, so that's easy, but way simpler than trying to figure this out using epsilon delta. What if we had the limit as x approaches 1 of f of x, g of x? So here we can rewrite this as the limit of f of x, the limit of g of x. Or can we? What's the limit of f of x at 1? The limit of f of x at 1 is 1. The limit of g of x at 1, it depends on which direction you go, right? If you're coming at it from the left, it's -2. If you're coming at it from the right, it's -1. That means that the limit of g of x at 1 does not exist. So since the limit of g at 1 doesn't exist, we can't use the product rule here, okay? And then let's look at one more. What about the limit of f of x over g of x as x approaches 2? Well, we want to use, of course, the quotient rule. But the limit of g as x approaches 2 is 0. That means that we cannot use the quotient rule here. So this one also we can't do. It doesn't mean necessarily that this limit doesn't exist. Maybe it does, but we can't use the quotient rule to figure it out. So the point of these examples is just that there are conditions on these rules, okay? Don't be too casual about using them, because you need to make sure that the conditions are met, meaning that the limits of both f and x have to exist at a, and the limit of g for the quotient rule can't be 0. Okay. So now, if we apply the product rule over and over with g of x equals f of x, then we get the next rule. So the power law is that the limit of f of x raised to the n equals the limit of f of x, the whole thing raised to n, with n a positive integer. To use these rules effectively, we need two more special limits, which are that the limit as x approaches a of a constant equals the constant, and the limit as x approaches a of x equals a. And both of these are obvious. If you just draw a graph of the function c, then obviously no matter what x is, it's going to approach c, right? And if you have the function that f of x equals x is just this line, so obviously no matter what x is, if this is a, then f of x is going to be a too, right? That's obvious. But we can prove it using the epsilon delta. If you want to, again, let me know in the comments and we can prove those. And now if we make f of x equal x in the power law, and then we use rule 8, then we get another good rule, which is that the limit of x to the nth power equals a to the nth power, where n is a positive integer. And there's a similar one for roots. The limit as x approaches a of the nth root of x equals the nth root of a if n is a positive integer, and if n is even, then we assume that a is greater than 0. That's because, for instance, square roots only work if the x, right, if this is the square root of x, then x has to be greater than 0, because otherwise the answer is complex. And then there's a generalization of this. So the limit as x approaches a of the nth root of fx equals the nth root of the limit of fx, where n is a positive integer, and then again, if n is even, we assume that the limit as x approaches a of f is greater than 0. This last one would be a little more difficult to prove, and we will prove it after we've looked at continuity. Okay, those are the limit laws. Okay, so let's do some examples. Let's find the limit as x approaches 5 of 2x squared minus 3x plus 4. Okay, so using our laws, that's going to equal limit of 2x squared minus limit of 3x plus limit of 4. These are all as x approaches 5. This is the difference law, and then this is the sum law. And then here's a constant we can take out. So it's 2 limit x squared minus 3 limit x, and then plus limit 4. And now we can use laws 7, 8, and 9. So law 9 says that the limit of x squared equals a squared, and it says x approaches 5. So this is just 2 times 5 squared minus 3 times 5 plus the limit of c equals c, so that's 4. So it's 50 minus 15 is 35 plus 4 is 39. What about limit x approaches 2 of x cubed plus 2x squared minus 1 over 5 minus 3x? So we're going to start by using the quotient law. So we have the limit of x cubed plus 2x squared minus 1 over the limit of 5 minus 3x. Again, all as x approaches 2. But it's important to remember that the quotient law has a restriction that the limit of the denominator does not approach 0. So we don't know yet whether that's going to be true. We're going to have to take a few steps before we can find out whether any of this is legitimate or not. But just remember that we can't do this if the limit of 5 minus x3 equals 0. So moving on, now we can distribute through the limit x cubed plus, and I'll do the constant law too, limit x squared minus limit 1 over limit 5 minus 3 limit x. And now we can just use 7 and 9 again. So we have, as x approaches 2, this is 2 cubed plus 2 times 2 squared minus 1 over 5 minus 3 times 2. So now we can see this is going to be minus 1. Well, I almost got done without making a mistake, but here this is 8 plus 8 is 16, minus 1 is 15, and this is minus 1, so it's minus 15. Okay, good. So notice one thing about these examples. If we had just plugged 5 in directly, we would have gotten 2 times 5 squared minus 3 times 5 plus 4. That's 50, 35, 39. So we could have skipped all the limit stuff and just plugged this in directly. And it's the same thing here. If we just plug these in, it's 2 cubed plus 2 times 2 squared minus 1 over 5 minus 3 times 2 is 8, 16, 15 over minus 1 is minus 15. And the functions here, this is a polynomial, and this is a rational function, which is a polynomial over a polynomial. And we can actually state one more rule here, which is that if f is a polynomial or a rational function, and a is in the domain of f, then the limit as x approaches a of f of x equals f of a. So f here can be a polynomial or a rational function. And notice that this will only work if the denominator is not 0. And that's actually taken care of by this part, because we're only looking at a if it's in the domain of f. So if a is not in the domain of f, then this rule doesn't work, okay? In a couple videos, we're going to talk about continuity, one interesting fact about this rule is that it's another formulation of continuity. Functions with the direct substitution property are continuous at A. So that's interesting. But remember, not all functions are continuous. Polynomials are, and rational functions are in their domain, but not all functions are. Example. Find the limit as x approaches 1 of x squared minus 1 over x minus 1. So if we let f equal this part, then the rule that we just stated does not work here because 1 is not in the domain of f, because 1 minus 1 is 0, so f of 1 is undefined. And also notice that we can't apply the quotient rule here either, because the limit of x minus 1 as x approaches 1 is 0. And also notice, by the way, that the quotient rule and the direct substitution rule do not have the same restrictions. The quotient rule says that the limit cannot be 0. The direct substitution rule only says that the limit has to actually be in the domain. So they're not quite the same thing, but in this case it fails both of them. And then it's also important to see that the fact that this problem fails both of those rules, that we're not able to apply either one of those rules to this problem, doesn't mean that the limit doesn't exist. It just means that we're not able to use those rules in order to just plug things in and find the answer. So we can do a little algebra though. X squared minus 1 over x minus 1. This again is the difference of two squares. So that's x plus 1, x minus 1 over x minus 1. So here again is where the subtleties of limits, it's important to keep them in mind, because it looks like we can just divide through and cancel both of these. But that'll only work if this does not equal 0, because we are not allowed to divide by 0. But the important thing here is that we're looking at the limit as x approaches 1. We're not actually looking at where x equals 1. So we can divide here, because no matter how small x gets, it's never going to be quite 1. So it is legitimate in this case to cancel them. So the algebra is legitimate, even though the quotient rule won't apply in this case. So then we just have that the limit as x approaches 1 of x plus 1 equals 1 plus 1 equals 2. So one interesting note here is that this is actually what this problem is the parabola y equals x squared at the point 1, 1. This is the derivative of this function at this point. Because what is the derivative? It's the slope of this line as the point gets closer and closer to 1, 1. So the angle gets closer and closer to the tangent, right? And so if we take a point that's away from 1, 1, this point would just be x, x squared, right? And then this point is 1, 1. So if we want the rise over the run of the angle from this point to this point, we would have the difference from x squared to 1 over the difference from x to 1. So that's the derivative. And then as x, x squared approaches 1, 1, it's going to get closer and closer to the tangent. Okay, let's do one more example. So let's find the limit as t approaches 0 of the square root of t squared plus 9 minus 3 over t squared. So again, once again, we can't apply the quotient rule directly because the limit of t squared as t approaches 0 is 0. So we're going to have to do something else. So let's try some algebra to get the denominator to be not 0. What we can do is put the radical in the denominator by rationalizing the numerator, and you do that by multiplying by the conjugate here. So if we have always here limit as t approaches 0, okay, so we're multiplying by the conjugate of this one, and that equals, so now it's the difference of two, we end up with the difference of two squares. So these are squared, so we have t squared plus 9 minus 9 on top, and t squared times on the bottom. So these cancel, and then with only t squared on the top and the bottom, we can cancel that, and we have the limit as t approaches 0 of 1 over. So now, as t approaches 0, this is not 0. So we can apply the quotient rule and then the constant rule to say that the limit of 1 is just 1. So we have 1 on top, and then the limit of this on the bottom. Then we can apply the sum rule, so we'll have the limit of the square root of t squared plus 9 plus the limit of 3, and then we can use the quotient rule to move the limit inside of the radical. So we end up with radical limit of t squared plus 9 plus, and then this is the constant rule, so just plus 3. And now the limit of this as t approaches 0 is going to be the limit of t squared is just 0. The limit of 9 is just 9. So it's the square root of 9 plus 3 equals 1 over 3 plus 3. When you get comfortable with these rules, you don't need to spell them out. Like, clearly this is just put the limit on the top and the bottom. You can move the limit inside and so on. But the important thing to remember is always to make sure that all of the conditions for the rules apply. So you can't apply the quotient rule until you know that the limit of the denominator will not be 0 and so on. And you also have to make sure that all of the limits in fact exist. But in this case, that's easy. So, okay. And one other thing, this is obviously hard. Or the math isn't hard, but it's hard to come up with this on your own. And the thing to remember is that the problems that teachers give you, they've always been worked out in reverse. So you come up with a problem that will involve the root law, and then you make it a little more complicated, and then you present the problem. This one's designed to be easily doable with the conjugate in order to move the radical down to the bottom. In real life, if you're just confronted with a problem that wasn't invented in the lab, it would be much more difficult even to come up with this, possibly. This is just facility with algebra that in real life, it might take a lot of trial and error in order to get it right. So in cases like this, if you don't see it right away, don't feel bad, because the person who invented this problem went in reverse. They wanted to use the root law, so they knew what the end looked like, and then they added complications going up so they can look impressive when they're presenting the problem to you. Okay. So sometimes the best way to find the limit is with the left and right hand limits. So remember this rule, that the limit as x approaches a of f of x equals L if and only if the right hand limit equals L and the left hand limit equals L. So the important fact is that all of the limit laws hold for one-sided limits as well. So example, show that the limit as x approaches 0 of the absolute value of x equals 0. So remember, the absolute value is x if x is greater than or equal to 0, minus x if it's less than 0. So since the absolute value of x is x when x is greater than 0, then we have the limit as x approaches 0 from the right of the absolute value of x equals the limit as x approaches 0 from the right of x, and that equals 0 from law 8. And the limit as x approaches 0 from the left is just the limit of minus x. That equals minus the limit of x, and that again equals 0. So the left hand and the right hand both equal 0. So the limit as x approaches 0 of the absolute value of x equals 0. Okay? And just to show you the graph of this, this is the absolute value of x when it's positive. This is when it's negative, and there's 0. So they do, in fact, it's a sharp corner, but it's definitely continuous right there. Okay, so contrast that to prove that the limit as x approaches 0 of the absolute value of x over x does not exist. So the limit coming from the right of the absolute value of x over x is just x over x. That equals 1, and so the limit as x approaches 0 of 1 is 1. Approaching it from the left, x is now minus. So the absolute value equals the opposite of x, which is going to be minus over x. So then we can take the minus out, and then x over x is still 1. So the limit here is minus 1. So these don't equal, so that proves it. The limit doesn't exist, because coming from the left and the right, they're not the same. The graph of that looks like this. It goes straight into 0 at -1, and then it jumps up to 1, so there's no limit here. Let's look at one more example. If f of x equals the square root of x minus 4 if x is greater than 4, and 8 minus 2x if x is less than 4, determine whether the limit as x approaches 4 of f of x exists. Okay, so again, let's look at the one-sided limits. So if we look as x approaches 4 from the right, then we have the square root of x minus 4, and that equals the square root of 4 minus 4 equals 0. So here again, this is one of those situations. It shows one of the million little details about limits that make them difficult. You have to be very careful, even when it looks simple, because the root law says that what's inside the radical has to be bigger than 0. It has to be positive. So we can't use the root law here because the limit as x approaches 4 of 4 minus 4 is 0. But we proved in the last video that the square root of 0 is 0. So we're just going to be able to use that fact to say that 4 minus 4 is 0 here. But we can't actually use the root law here. But that's why it's important to use the one-sided limits here, because we can't come at this radical from both directions, because if we're coming at 4 from the left, that makes this minus, which means that this wouldn't exist in the real numbers. So again, you have to be careful. We're not actually allowed to use the root law here because the limit of this is 0. And then as for the other side, when x is less than 4, it's 8 minus 2x. And then that just equals 8 minus 2. So here we just used the difference law again, and then the constant multiple law, and then law 8. So x just equals a, and so 8 minus 8 is 0. Okay, so 0 equals 0, so yes, this limit does exist. And what this function looks like at 4, it kind of comes down here from the negative, and then it goes up like that. But they do meet right here. It doesn't exist at 4, but both of the limits still equal 4. So the limit at 4 does exist. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.